A very basic technique that's found in virtually any laboratory doing molecular biology is that of gel electrophoresis. Many of you probably have run gel electrophoresis. Gel electrophoresis involves having a medium that through which molecules are sort of forced through. And that medium has what I describe as sort of pores through which molecules can fit. Those pores can be big holes through which big molecules can fit, or they can be tiny holes through which bigger molecules have a harder time fitting. And the key isn't the size of the holes really as much as it is the driving force that's pushing them through. So before I talk about that driving force, I want to say a little bit about different types of setups that we have here. So gel electrophoresis involves gels and it involves electricity. So there are two primary kinds of gels. And by the way, when do I do gel electrophoresis? I do gel electrophoresis when I have very big molecules to separate from each other. And very big means nucleic acids, proteins. That's really what we're talking about when we're doing gel electrophoresis. So we have to have pretty good sized pores. These are bigger than tiny proteins or something like that. For separating nucleic acids, we commonly use a support system that's called agarose, and agarose has pretty big pores because nucleic acids are quite a bit bigger than DNAs are. If we're separating proteins, most commonly we use something that has a smaller pore size, and that would include polyacrylamide, and so that's called polyacrylamide gel electrophoresis. For the moment, we'll not be concerned about which of those are there, and I'm going to talk about the separation of DNA molecules, okay? And specifically, I'll be talking here about on an agarose gel. To separate DNA molecules, we have an agarose gel, and we load our samples at the very head of the gel. At the very head of the gel, we place an electrode, and that electrode that's placed up at the head of the gel is a negatively charged electrode, so that the negatively charged nucleic acids that are there are repelled by the negative electrode. Nucleic acids are negatively charged because they have a phosphate backbone, and phosphates ionize to form a negatively charged molecule at physiological pH. Well, the negatively charged DNAs are driven away from the negative electrode, and they're driven in the direction of the positive electrode, so that electrical field is the driving force that's moving the nucleic acids through this agarose sets of pores. Not surprisingly, nucleic acids that are smaller find it easier to navigate through those pores, and they move faster, whereas larger nucleic acids have a harder time moving through those pores, and they travel slower. So in gel electrophoresis, the molecules that are the smallest molecules travel the fastest, and those that are the largest travel the slowest. The molecules move in the direction of the positive electrode and away from the negative electrode. In the case of proteins, there are other considerations. Now, the considerations include the fact that proteins can have a variety of charges, and proteins are all bundled up, whereas nucleic acids we could think of as rods. And rods are easier fixed structures than bundled up proteins. So to separate proteins by gel electrophoresis, we've got to first of all give them a uniform charge, and second, we need to unbundle them and let them be more like rods. Well, both of these are accomplished in gel electrophoresis by adding the detergent SDS, sodium dodecyl sulfate. Sodium dodecyl sulfate takes a protein that, for example, might have been like so, and it denatures it. So when it denatures it, it turns it into a rod, and that rod, interestingly, becomes coated with the SDS, where these individual things here are the SDS. Now, SDS is sodium dodecyl sulfate, and sulfates have a negative charge. So every one of these guys has a negative charge. That negative charge now becomes a driving force that allows the electrical system that I talked about for gel electrophoresis to push away from the negative electrode and towards the positive. And the individual charges that are on the inside here of the protein don't usually enter into the equation. So as a result of SDS polyacrylamide gel electrophoresis, or SDS PAGE as people call it, proteins can be separated on the basis of size.